graphing rational functions, like I mentioned, without relying upon our calculator, especially if you have any plans of ever taking calculus in your life, whether it's with me or in college, you're gonna have to know this stuff about rational functions without your calculator, okay? So there's several things that we must find and graph. So the first few we've kind of already covered how to find those. Number one, the horizontal asymptote. We graph that as a dotted line, a horizontal dotted line. Our holes. We graph those as an open circle, and that's why I've been having you find the x and the y, because we have to put where that point actually would be. Our vertical asymptotes are dotted lines, they're just vertical. The slant asymptote, the same thing. We want to graph that as a dotted line. Here's what we haven't talked about yet. Our x-intercepts, those come from setting the simplified numerator equal to 0. That's where x-intercepts come from. Our y-intercept comes from plugging in 0 for x, okay, as long as x equals 0 is not a vertical asymptote. That happens sometimes. And then the last thing that we need to do is we need to determine our behavior around the vertical asymptote, okay? So that's kind of the list we're going to go through every time. So here's the first example, okay, that we're going to go through and we're going to find everything for. We've got 2x squared minus 2x minus 12 over 3x squared minus 12. And y'all might like some graphing numbers to work on. Oh, yes. While y'all are running out the problem, when starting the factoring process, okay, start the process of factoring here. So that we can find all of the things that we need to find to be able to graph this. Alright, I've got more graph paper if anybody needs it, just give me a holler. Okay, don't use the entire front side on problem number 1. Okay, so when we start this factoring process, what do we need to start with? GCF out of the numerator. Okay, go ahead and take a GCF out of the denominator as well. Okay, so in the numerator it was a 2, in the denominator it's 3. Both of those will factor further. The top is x minus 3 times x plus 2. And the bottom is x plus 2. Whoa, I don't know what that is. X plus 2, not x squared. I was very pleased on the test. Most of you remembered to factor that grouping problem, to factor it further. You recognize the difference of perfect squares, which I was very happy with. Okay. So there's the fully factored version. Let's go down our list here. Do we have a horizontal or a slant asymptote? Horizontal, what is it? Y equals 2/3. Okay, y equals 2/3. So let's go ahead and as we're doing this, and I have these color coded for a reason, y equals 2/3. Let's go ahead and put our horizontal line, our dotted horizontal line at 2/3. Now, hopefully your graph will turn out a little bit better than mine. We're gonna get a little cramped here, but that's all good. Don't forget, there's a small ruler in your pencil box. If you're one of those OCD people and you want a perfectly straight line, you just have to share it because there's just one per group. Okay, so we got the horizontal asymptote. Do we have a hole? Yes, we do. Okay, because x plus 2 is going to cancel in the numerator and in the denominator. So we know that our hole is at x equals -2, but we've got to find the y value as well. So let's plug -2 into what we've got left. Negative 2 minus 2, so that's negative 2 minus 3 is negative 5, so we got negative 10 on the top. Negative 2 minus 2 is negative 4, so we got negative 12 on the bottom. Negative over negative is a positive. Both of those are divisible by 2, so we get 5 over 6. So at negative 2, 5, 6, we are going to put an open circle. Now this is where I was talking about mine's going to get real cramped. 5 over 6 is greater than 2/3. How do I know that? Because 2/3 is 4/6. Multiply top and bottom by 2, you get 4 over 6. So 5 over 6 is bigger than 2/3, so it needs to go above our dotted line, but it's not quite 1. So you kind of got to squeeze it in there between your horizontal line and y equals 1. Okay? A lot of people will forget to find the y value, and so for whatever reason, they put the open circle on the x-axis. That's not where it goes. Okay? You have to actually put the point on there. Okay? All right. Vertical asymptote. Do we have one? Yes. What is it? X equals 2. Okay? Speak up. Y'all acted like you knew what was going on with the warm-up there. Okay? X equals 2, so put you a vertical dotted line at x equals 2. Now, for our x-intercepts, we take the simplified numerator and set it equal to 0. Well, we don't have to worry about the 2 part, because 2 doesn't equal 0. All we have to worry about is the x minus 3, so our x-intercept is at 3, 0. Please write it as a point. 3, 0 is our only x-intercept. Our y-intercept, we plug 0 into the equation. Now, here's where sometimes it's easier to just go back to the original to plug in 0, because we know that if we plug in 0, that's going to be 0, that's going to be 0. We've just got negative 12 in the numerator, and we've just got negative 12 in the denominator. So negative 12 over negative 12 simplifies to 1. Okay, you could have gotten the same thing if you plugged it into the factored version. You just have to multiply. 2 times negative 3 is negative 6. 3 times negative 2 is negative 6. Negative 6 over negative 6 is 1. Either way, you get to the same thing. All right, now, behavior around the vertical asymptote. Okay, so we only have this one vertical asymptote. On one side, we've got to figure out what's happening on the left side of it, and we've got to figure out what's happening on the right side of it here. So, I told you we're trying to do this as much as possible without a calculator. So here's how we're going to determine this. I'm going to rewrite my simplified function here. Okay, I'm going to rewrite the simplified part of my function, and I'm going to show you what we're going to do. All right, so I need to talk about the left side of the vertical asymptote. Well, what is a good number to the left of 2? Don't pick a whole number, okay? But what would be a fairly easy number to plug in to the left of 2? That's not a whole number. Like 1.5, right? Which would be, let's just go with 1.5. Okay, plug in the decimal. So I'm going to do this. I'm going to say left. I'm going to plug in 1.5. Now, here's the thing. I don't really care what that number ends up being. What I do care about is it positive or is it negative? All right? So if I do 1.5 minus 3, I don't want to know what the actual value is, but is it positive or negative? Negative. And when I multiply by positive 2, it's still going to be negative. Okay? How about on the bottom? It's also negative, right? 1.5 minus 2 is negative. Multiply by a positive number, it's still negative. A negative over a negative is positive. Okay? So what I have just convinced myself of is that on the left side of this vertical asymptote, my function is going to positive infinity because I got positive when I plugged in that number. that was close to my vertical asymptote on the left side. Okay? How about we plug in 2.5 for the right? Okay, the right, we're going to plug in 2.5. So what do we get on the top, negative or positive? Negative. How about on the bottom? Positive. So a negative divided by a positive is a negative. So on the right side, our function is going to go to negative infinity. Okay, that's what I'm talking about when I'm talking about the behavior around the vertical asymptote. Because around an asymptote, it's headed to either positive infinity or negative infinity. It's getting really close to it. It'll never touch 2, but it's getting really close to it. So pretty much at this point, I've got enough information that I can kind of connect the dots, so to speak. Okay, I'm going to connect my behavior around my vertical asymptote to my y-intercept there, to my hole. Now don't just run through the hole. Make sure you kind of pause and don't fill in that circle. And then my function is going to follow along that horizontal asymptote, because that's what a horizontal asymptote does. It tells us what the function's doing for its end behavior. And then I'll do the same thing on the right side. Connect my vertical asymptote behavior to my x-intercept, and then I'm going to follow along. Don't trace over the line. I know I got a little too close, but you want to get really close to that horizontal asymptote. Don't cross it, just get really close to it. Now, on the final exam, you have access to your calculator. If they're asking you to graph a rational function, or even if I do it on a test, if I'm asking you to graph a rational function, you can type it into your calculator and look at the graph and compare the answer choices if it's multiple choice. Now with mine, this would be a free response question, so you would have to accurately graph all these pieces right here, but you would still have your calculator to be able to confirm. Okay, now let's talk about that for a second. I mentioned this several times, but make sure that you put parentheses around the entire numerator divided by parentheses around the entire denominator. Okay, you got to make sure those parentheses are in there, or it's not going to give you the correct graph. All right, so again, several things I don't like about the graphing calculator. It makes that vertical asymptote. It looks like these two pieces are connected. They are not. Okay, this vertical asymptote separates those two parts, and it's a vertical dotted line. Okay, it doesn't show you the horizontal asymptote, but I want that on your graph. It doesn't show you the hole either on the graph. It does show up in the table. Okay, it does show up in the table as an error at 2 for the vertical asymptote, at -2 for the hole. Okay? All right. Yes, sir.
On the word that you get the vertical asymptote,
yes.
How did you get it? Or no hole?
For the hole. Okay.
How did you get the top and bottom?
Okay, so it came from my simplified version. See that part? Okay. So then I plugged in -2, and -2 times -3 is -5. -5 times 2 is -10. Okay. Yes, sir. -2 from, I canceled x plus 2. So when I solve that, that gives me -2. Okay. Good questions. No problem. Okay. Anything else on this one? Let's look at another example. Okay. Let's look at another one. -4 over x squared minus 3x. -4 over x squared minus 3x. I realize that a lot of this it should look familiar. We've done it in Math 3, but not everybody remembers everything. So the numerator obviously does not factor. Okay, I know we can factor -4, but you know what I mean. The bottom, we can pull out a GCF of x. So clearly nothing's going to cancel here. So we don't have a hole. Okay? So we can go ahead and say no hole. All right, horizontal asymptote or slant asymptote. What we got? Y'all got to know these rules. So horizontal or slant or none?
0.
Y equals 0. Okay, y equals 0. Because The numerator doesn't even have a variable. It's degree 0. The denominator is degree 2, so the denominator is definitely higher degree. So y equals 0 is the x-axis. Okay, y equals 0 is the x-axis. So if you run into that case, you've just kind of got to go over the x-axis with a thicker dotted line. Okay, so that's what I've done here. I've made my line a little bit thicker so that I can clearly see that y equals 0 is the horizontal asymptote. Okay, how about vertical asymptote? What are we looking at? We've got two of them, right? We've got x equals 0, and we have x equals 3 from setting the denominator equal to 0. Well, here's the same thing. X equals 0 is the y-axis. So we've just got to emphasize it, make it a little bit darker so that I can see that you've got the y-axis as a vertical asymptote and it's not just your axis. Okay? All right. So x-intercept. Set the numerator equal to 0. Well, what's in the numerator? -4. -4 does not equal 0. We do not have an x-intercept. These do not have to have x-intercepts, just like they don't have to have a hole, or they don't have to have a vertical asymptote, or they could have two. You can have any combination of these things. Okay? So in this case, this one doesn't cross the x-axis. How about a y-intercept? We got to plug in 0 for y. We got to plug in 0 for x. What happens when we plug in 0 for x? We get 0 in the denominator. Is that a good thing? No, that is undefined. We do not have a y-intercept either because x equals 0 is a vertical asymptote. You cannot touch or cross vertical asymptotes. So if this is a vertical asymptote, you can't do anything, okay? It can't be a y-intercept. So we don't have any points. All we have are our vertical asymptotes and our horizontal asymptote. So we don't have anything to connect here. If we're trying to do this completely without our calculator, we don't have any points to connect. Let's talk about our behavior around our vertical asymptote. Let's talk about the left of 0. So let's plug in, what, -0.5? So we've got a negative on the top always over a negative times a negative. If we plug in -0.5, x is negative, x minus 3 is negative. So if we've got 3 negatives, what's the result? Negative. Okay, so to the left of 0, we're going to negative infinity. Let's check the right. Okay, so plugging in positive 0.5. We've still always got a negative on top because it's -4. Okay, x is now positive. 0.5 minus 3 is going to be negative. So negative over a negative gives us positive. So to the right of 0, we're going to positive infinity. We've got another vertical asymptote. We've got 2. So the left of 2, or excuse me, 3, not 2. I was thinking of the last problem. Left of 3. So plug in what? 2.5. Top is always negative. We've got positive x. 2.5 minus 3 is negative. So that gives us a negative infinity. Right? Yep. Okay. The right of 3. Top is always negative. X is positive. Something bigger than 3 minus 3 is going to be positive. So this is also negative. No, I screwed up that last one. That last one should be positive, shouldn't it? Negative over a positive times negative is positive. Sorry. Thought that looked weird. And nobody said anything. Y'all know I make mistakes too. I'm not beyond admitting it. Okay, so I still don't have a lot of detail here. I really don't have a lot of detail. So I'm gonna kind of cheat and use my calculator on this one. Oh, she made a mistake and she's gonna cheat. What is happening? So I'm gonna go to my table first. Okay, I'm gonna go to my table first. I'm not gonna go straight to the graph because I just want to plot some points here. -1, -1, -2, -0.4. Okay, so that gives me something to go off of. I can connect my behavior around the vertical asymptote to these 2 points, and I can see that my y values are getting closer and closer to 0 here if I kept on going. Okay, see how close they're getting to 0? Let's see here. 0, 1 is 2, and 2 also gives us 2. So actually what's going on here, we kind of have a little parabola going on right here. Okay, right there in the middle. And then 4 is -1. And 5 is -0.4. That's interesting. There's some symmetry going on here. Okay, that's what this rational function is going to look like. Okay, so with these examples, I was trying to give you a good variety of the different types of rational functions you'll run into. Okay, most of them have just those 2 curves, but when you have more than one vertical asymptote, it's going to give you more pieces. Okay, every time you have a vertical asymptote, it's going to break it up. You're going to have another piece to your graph. Okay, all right, I think I've got one more here, because we haven't done with the slant asymptote, right? Yeah. Okay, so we've got x cubed minus 9x over 3x squared minus 6x minus 9. So we haven't done the slant asymptote. Clearly you can see my slanted line over here, so probably good indication that this one is a slant asymptote, right? Okay, so do y'all want to find the slant asymptote first, or do you want to factor? Factor? Okay, we'll go with factoring first. Take out an x from the numerator. Take out a 3 from the denominator. Factor the difference perfect squares in the numerator. Factor x minus 3 times x plus 1 in the denominator. Okay, so let's deal with the slant asymptote next. So long division. What's on the bottom goes outside the house. What's on top goes under the house. Notice we're missing some powers. Put some placeholders in there or it's going to mess you up. Okay, x cubed divided by 3x squared. Oh darn, there's one of those fractions again. 1/3 x. That gives us x cubed minus 2x squared minus 3x. Isn't it funny though how they always work out after that? So the x cubes cancel. We get positive 2x squared when we add. And when we divide here, we get plus 2/3. Remember, we don't have to finish out the division. We can stop right there. 1/3 x plus 2/3. So y-intercept 2/3. Go up 1 over 3. Okay, up 1 over 3 from y equals 2/3. Or, yeah, the y-intercept is 2/3. Okay, do we have a hole? Yes. Where is it at? 3, positive 3. Okay, how about, let's figure out the y part. So we've got 3 times 3 plus 3 over 3 times 3 plus 1. Guess what? I can cancel those 3's. So 3 plus 3 is 6, 3 plus 1 is 4. Divide those both by 2. So 3/2, or 1.5. So 1, 2, 3. 3 and 1.5. Okay, that is below the slant asymptote there. Okay, just below it. Okay, vertical asymptote. Do we have one? Vertical asymptote. Yes? No? Maybe? We don't know? We don't want to answer? Yeah, we got one. All right, where's it at? -1. Thank you. Sometimes like pulling teeth with y'all. All right, x equals -1 is our vertical asymptote. Okay, how about an x-intercept? Where does the x-intercept come from? Set in the numerator equal to 0. So we've got two pieces left in the numerator. We've got x equals 0, and we have x plus 3 is equal to 0. So we've got 0 and -3. Well, guess what? Since our x-intercept was at x equals 0, that's also our y-intercept, okay? Because that's when if x is 0 and the y equals 0, so that's also our y-intercept, okay? Now, hopefully at this point, you've seen enough of these that you kind of could just go ahead and fill in your graph, okay? You follow the asymptotes, you get really close to them. All right, and you connect your points. So that's your general sketch of the function. But if you weren't entirely trustworthy of that, let's go through the behavior around the vertical asymptote one more time in case you don't have it yet. So left of -1. So let's pick a number to the left of -1, like -1.5. So the numerator, we've got x, so that we know that's negative. Okay, what do we get when we do -1.5 plus 3? Positive or negative? Positive. Okay, so we've got a negative times positive on the top. On the bottom, 3 is always positive, and -1.5 plus 1 is negative. So negative on top, negative on the bottom, that overall gives us a positive infinity. Well, I already sketched that. To the left, I went up. Okay. To the right of -1, okay, so -0.5. So x is a negative number. -0.5 plus 3 is going to give us a positive. 3 is always positive. And -0.5 plus 1 is positive. So we've got a negative over a positive, which is negative. So to the right, our function is going down. Okay? Make sense? Did I totally blow your minds with this part, or does it kind of make sense? It's the easiest part. Yes.
I have understood this one time. It says right over going negative. What part?
Right of -1. So here's our vertical asymptote -1. I'm talking about to the right of it.
Don't you go left to right?
Yes, you move left to right, but we're trying to figure out on the left side of this vertical asymptote, where are we going? Or why are we going up here? Positive. To the right, on the right side of it, right next to it, you're going to negative. We're just talking about like right, so we're focusing right close to the vertical asymptote there. Okay? All right. So I think that was all I had. Yes. Okay. So here's what I want you